Hello, this is Ian Zaun
Chris Vu.
and we are doing vectors. Let's start off. Vectors will show up all over the place in our study of physics. Some physical quantities that are presented as vectors are displacement, velocity, acceleration, force, and momentum.
A vector is a quantity that involves both magnitude and direction. It obeys the commutative law for addition, which we'll explain later. A quantity that does not involve direction is a scalar. For example, the quantity 55 miles per hour is a scalar, while the quantity 55 miles per hour to the north is a vector.
Vectors can be denoted in several ways, including the vector sum a plus b means the vector a followed by b, while the vector sum b plus a means the vector b followed by a. A vector can be multiplied by a scalar, that is a number, and the result is another vector.
If the original vector is a and the scalar is k, then the scalar multiple of ka is as follows. Magnitude of ka equals the absolute value of k times the magnitude of a. Direction of ka equals the same as a if k is positive, the opposite of a if k is negative.
Let's try an example. Let's try to sketch the scalar multiple of 2a, 1/2 a, negative a, and negative 3a.
And here they are. Vector subtraction. To subtract one vector from another, for example, to get a minus b, simply form the vector negative b, which is the scalar multiple of negative 1 times b, and add it to a, as shown.
For the two vectors, a and b, find the vector a minus b. For the solution, flip b around, thereby forming negative b, and add that vector to a.
Standard basis vectors. Two-dimensional vectors, that is, vectors that lie flat in the plane, can be written as a sum of a horizontal vector and a vertical vector. For example, in the following diagram, the vector a is equal to the horizontal vector b plus the vertical vector c.
The horizontal vector is always considered a scalar multiple of what's called the horizontal basis vector, I, and the vertical vector is a scalar multiple of the vertical basis vector, j. Both of these special vectors have a magnitude of 1, and for this reason, they're called unit vectors.
Unit vectors are often represented by placing a caret over the vector. For example, the units vector I and j are sometimes denoted I hat and j hat.
For instance, the vector a in the figure below is the sum of the horizontal vector b equals 3i hat and the vertical vector c equals 4j hat.
The vectors b and c are called the vector components of a, and the scalar multiples of I hat and j hat, which give a, in this case 3 and 4, are called the scalar components of a. So vector a can be written as the sum a sub x I hat plus a sub y j hat, where a sub x and a sub y are the scalar components of a. The component a sub x is called the horizontal scalar component of a, and a sub y is called the vertical scalar component of a.
The use of components makes the vector operations of addition, subtraction, and scalar multiplication pretty straightforward.
Vector addition. Add the respective components.
A plus b equals parentheses a sub x plus b sub x and parentheses times I hat plus start parentheses a sub y plus b sub y and parentheses times j hat.
Vector subtraction. Subtract the respective components.
A minus b equals start parentheses a sub x minus b sub x and parentheses times I hat plus start parentheses a sub y minus b sub y and parentheses j hat.
Scalar multiplication. Multiply each component by k.
Ka equals start parentheses k times a sub x and parentheses times I hat plus start parentheses k times a sub y and parentheses j hat. Let's see an example. If a equals 2 times I hat plus 3 times j hat and b equals 4, negative 4 times I hat plus 2 times j hat, compute each of the following vectors: a plus b, a minus b, 2a, and a plus 3b.
It's very helpful that the given vectors a and b are written explicitly in terms of the standard basis vectors I and j. Here are the 4 solutions. Look at them carefully.
The magnitude of a vector can be computed with the Pythagorean theorem. The magnitude of A equals A sub x times I hat plus A sub y times j hat. It's given by the equation A equals the square root of A sub x squared plus A sub y squared. This is the formula for the length of the hypotenuse of a right triangle with side lengths A sub x and A sub y.
For the direction of a vector, the direction of a vector can be specified by the angle it makes with the positive x-axis. You can sketch the vector and use its components and an inverse trig function to determine the angle. For example, if theta denotes the angle that the vector A equals 3i hat plus 4j hat makes with the x-axis, then tangent theta equals 4 over 3, so theta equals inverse tangent 4 over 3 equals 53.1 degrees. Make sure your calculator is in the correct mode, either radian or degree, when using trig functions.
If A makes the angle theta with the x-axis, then its x and y components are A cosine theta and A sine theta respectively, where A is the magnitude of A vector. A equals A cosine theta times I hat plus A sine theta times j hat.
Any vector in the plane can be written in terms of two perpendicular component vectors. For example, vector W, shown here, is the sum of two component vectors whose magnitudes are W cosine theta and W sine theta.
The dot product. A vector can be multiplied by a scalar to yield another vector. We can multiply the vector A by the scalar 2 to get the scalar multiple 2A. The process is a vector that is twice the magnitude, and since the scalar is positive, it is in the same direction as A. Additionally, we can form a scalar by multiplying two vectors. The product of the vector, in this case, is called the dot product or the scalar product. Several physical concepts require that we multiply the magnitude of one vector by the magnitude of the component of the other vector that's parallel to the first.
The dot product was invented specifically for this purpose. Consider these two vectors A and B. In order to find the component of B that's parallel to A, we do the following. As this figure shows, the component of B that's parallel to A has the magnitude B cosine theta. So if we multiply the magnitude of A by the magnitude of the component of B that's parallel to A, we will form the product A times B cosine theta. This is the definition of the dot product of the vectors A and B. A times B equals AB cosine theta, where theta is the angle between A and B.
Notice that the dot product of two vectors is a scalar. The angle between the vectors is crucial to the value of the dot product. If theta equals 0, then the vectors are already parallel to each other, so we can simply multiply their magnitudes. A dot B equals AB.
If A and B are perpendicular, then there is no component of B that's parallel to A or vice versa, so the dot product should be 0. And if theta is greater than 90 degrees, then the component of one that's parallel to the other is actually anti-parallel, backwards, and this will give the dot product a negative value, because cosine theta is less than 0 if 90 degrees is less than theta, which is less than 180 degrees.
The value of the dot product can, of course, be figured out by using the definition above, AB cosine theta, if theta is known. If theta is not known, the dot product can be calculated from the components of A and B in this way. The cross product. Some physical concepts, torque and angular momentum, require that we multiply the magnitude of one vector by the magnitude of the component of the other vector that is perpendicular to the first. The cross product was invented for the specific purpose. Consider these two vectors, A and B.
In order to find the component of one of these vectors that's perpendicular to the other one, we must do the following. As this figure shows, the component of B that's perpendicular to A has magnitude B sine theta. Therefore, if we multiply the magnitude of A by magnitude of the component of B that's perpendicular to A, we form the product A times B sine theta. This is the magnitude of what's called the cross product of the vectors A and B, denoted A cross B. The absolute value of A cross B equals AB sine theta.
The equation above gives the magnitude of the cross product. The cross product of two vectors is another vector that is always perpendicular to both vectors A and B, with its direction determined by the process known as the right-hand rule. The direction of A cross B is perpendicular to the plane that contains A and B, but this leads to ambiguity. Since there are two directions perpendicular to a plane, one on either side, they point in opposite directions.
Make sure you're using your right hand. Point your index finger in the direction of the first vector A, then point your middle finger in the direction of the second vector B, and your thumb now points in the direction of the cross product A cross B. This is called the right-hand rule. You know that the standard basis vectors I hat and j hat can be used to write any two-dimensional vector, but now that we have introduced the cross product, we need a third basis unit vector to write three-dimensional vectors. This third unit vector is denoted k hat, and like I hat and j hat, points along the direction of the coordinate axis.
The vector I hat is the unit vector that points along the x-axis, j hat along the y, and now k hat along the z. The three basis vectors are mutually perpendicular.
Unlike the dot product, the cross product is not commutative. A cross B is not equal to B cross A. This is because applying the right-hand rule to determine the direction of B cross A would give a vector that points in the direction opposite to that of A cross B. Therefore, B cross A is equal to negative A cross B.
The cross product can be computed directly from the scalar components of A and B without first determining the angle theta, as follows. If A equals A sub x times I hat plus A sub y times j hat plus A sub z times k hat, and B equals B sub x times I hat plus B sub y times j hat plus B sub z times k hat, and the cross product magnitude and direction of A and B is shown below.
This formula requires a lot of memorization. Another method of determining the cross product is to realize that the cross product is a determinant of the following 3x3 matrix, as shown below.
By taking the determinant of each 2x2 matrix, you will realize that you will get the same formula as shown above. This may appear to be equally difficult to memorize. However, you can just memorize two facts. Each 2x2 matrix is missing the column associated with the base vector that multiplies it, and the terms alternate in sign. Thank you for listening to our little spiel on vectors. This is Ian Zaun, and
Chris Vu.
have fun in physics. That was fun.